class, so now we're on 12.6, and we're going to look at different types of intermolecular forces. So there are different types of intermolecular forces, and depending on what they are, also depends that determines how strong these forces are. So the strength of the intermolecular forces between the molecules or atoms that compose a substance, and that is what makes the substances how we know them to be. Strong intermolecular forces result in solids and liquids. They tend to have high melting and boiling points. Weak intermolecular forces result in gases, and gases have low melting points and low boiling points as well. So we're going to look at dispersion, dipole, and hydrogen bonding in this section. So dispersion forces. Dispersion forces are all molecules and atoms have them. They have electrons, but electrons are constantly moving, and because they're constantly moving, there can be at any given time an unevenly distributed amount of electrons on one side over the other, and that creates a negative and positive charge within the atom or molecule itself. That's what these dispersion, they're also called London forces. And what happens is that these fluctuations in this electron distribution causes the attractions to other molecules, only for a moment. But I have a little GIF so you can see what happens. So as you can see, these the electrons are on one side, and because that means that it's negative on this side, it's positive on the other because there's nothing there. It forces the electrons in the other atom to be attracted to that, leaving it positive on that side. So this is called a temporary dipole. So that's what you see. The electrons are constantly moving. So if you look at a symmetrical distribution, you can see that these electrons are all spread out evenly. But when it's unsymmetrical, you see that here's the nucleus, and here is the electrons. So it's partially negative here and partially positive. And that causes another atom or molecule to come in due to the partial positive and partial negative ends of this. So again, this is just showing exactly that you can see that these are moving. They're constantly moving around, and this is an even symmetrical distribution of electrons, and then you see that it's not, and that's where you see we don't see the partial positive or partial negative on frame 1 or frame 2, but you do see it on frame 3, and this is what they call instantaneous dipole or temporary dipole. And remember, a dipole is just a separation of charge, and that's what you get with a positive and an negative. So you can see here's another one where you see the electrons moving and stuff. So the separation of charges, these instantaneous dipoles, are responsible for dispersion forces, and all atoms have them. Because they have electrons. So if they have electrons and these electrons can move, then these constantly happen, and they happen very quickly, and they go away just as quickly. So it's constantly happening with all these atoms and molecules. Some are attracted, some repel at the same time. That's what you're seeing here. So again, now you see these weak attractions because these electrons are moving, and it then adjusts with the other ones when they are moving, so they become more attracted to it or repel it away, depending on how these electrons are moving within it. So this is the dispersion forces. So the magnitude of the dispersion forces depends on how easily the electrons in a molecule can polarize. So remember, polarization or polarity is because of the electron, those partial positive and partial negative charges not canceling out. So there's an imbalance of these partial positive and partial negatives. They're not ionic because it's just the electrons, or the shape also has to help in not canceling out this polarity. So it also depends on the size of the electron cloud. So to polarize means to form a dipole, which is a separation of charge. A large electron cloud results in greater dispersion forces. So because of the electrons are held less tightly by the nucleus. So you have, what does that mean? That means they can spread out more. Think of a cloud. If something's holding on to something tightly, that cloud's going to be very small. But if it's holding onto it loosely, then it has more freedom to expand out, and when it can expand out enough, that means that it has a greater, it's not held as tightly, and it can polarize more easily. Molar mass alone also doesn't play, but molar mass does affect the magnitude of dispersion forces, and we'll look at that. But it can be used as a guide for comparing dispersion forces. So if we take a look here, there's one thing with the noble gases. We have a boiling point. Now, Remember what I talked about with intermolecular forces? Strong intermolecular forces have high melting points and high boiling points. Weak intermolecular forces have low boiling points and low melting points. So you can see as the molar mass, as these molecules get bigger, the boiling points also increase. So this is not necessarily an, that's what it says on the previous slide, that it doesn't determine the magnitude alone of the dispersion force, but it definitely helps. So when you see a bigger molecule, then you should know that it has a stronger intermolecular forces than something that's small. So let's take a look at this. What halogen, chloride or iodide, has a higher boiling point? Well, depending on where it is, we can determine, you can look at a periodic table or we can look at the masses. The molar mass of chloride with 77 diatomic chloride is, or chlorine I should say, is 70.90 grams per mole. But the molar mass of iodide is 253.80. So iodide has a higher molar mass, it has a stronger dispersion forces, and therefore a higher boiling point. And that is true. So dipole-dipole forces. Dipole-dipole forces exist in all polar molecules. So the key thing is in polar molecules. They have a permanent dipole. And remember, this is a permanent separation of charge. And they interact with permanent dipoles of other molecules, just like those other gifts were showing with dispersion. So not only do molecules have dispersion, some of them have dipole-dipole forces on top of that. So what it is the positive end of one permanent dipole is attracted to the negative end of another one. That's the attraction that holds these together. So on top of dispersion forces, some of these have dipole-dipole, and that's because these dispersions had an instantaneous or temporary dipole moment. These have a permanent dipole moment. They're not changing. They have this negative or positive, partial positive that's there. So these additional attractive forces raise the melting and boiling points relative to nonpolar molecules of the same mass. Because polar molecules have dipole-dipole and they have dispersion, where nonpolar do not have that. So what is a permanent dipole? So if we look at these here, we have formaldehyde, and you can see the structure here, and you can also see it in this nice, I forgot what they call this now, sorry. The positive end, it's going to bother me that I can't remember what this is, and I know it's not difficult. The positive end of a polar molecule is attracted to the negative end of a neighbor one. So why is this? This is because we have an oxygen, and remember electronegativity. Oxygen is the second most electronegative atom on a periodic table, so it's going to pull all the electrons away from the carbon, making this partial positive. So think of this, if you're sharing a blanket, this is taking all the blankets and you have one little corner and leaving you into the cold. So this is what's happening. Because this is partially negative, it's not going to attract the partially positive of the carbon onto it. And that's going to keep happening as these neighboring molecules come together. So effects of polarity on melting and boiling points for two similar compounds. So if we look here, it said that the additional attractive forces raise the melting and boiling points relative to nonpolar molecules of similar mass. So here we have two that are similar masses, but ethane is nonpolar. It's very symmetrical. It doesn't have in carbons and hydrogen, if you remember from chapter 10, they're almost very similar in electronegativity. So there's not big tug of war going on between them. In fact, we can kind of consider it negligible in this case. So if we look at formaldehyde, we can see that because it's got a permanent dipole, so it's got the permanent dipole, so dipole-dipole force, you can see that there's a difference. Negative 88 to negative 19.5. This is closer to 0 than this is for the boiling point. So this has a higher boiling point than ethane. Also, the melting point is at 172. This is negative 92. That's closer to 0. So the same thing applies. These are now two forces that this molecule has compared to the non-polar molecule. So now we're going to take a look at miscible. So this has to do with solubility. And this really is something that's not difficult to understand. There's a term, like dissolves like. So if you have something that dissolves in something else, then they are very similar. They have similar properties. If you have something that doesn't dissolve into something, then that is where like does not dissolve like. They are two different things. So miscible solutions in other solutions that are miscible means that they have the same properties. So then you get one layer. So if I add something like vinegar and water together, they will mix together because they are both polar. And because they're both polar, you'll only see one clear layer. You won't see anything else. However, if I add water with oil, I have two clear layers, and that means it's immiscible. So here's an example. A polar molecule is not miscible with pentane. Pentane is a hydrocarbon. It's very nonpolar. It has nothing that's really electronegative on it. But water is polar, so it's not going to. In fact, they're not going to mix no matter how much you shake them together. So here are some examples. Pentane does not mix with water, and you can see in A, the molecules will try to stay far away from each other. Think of like opposite sides of the room. B, the oil and vinegar in a salad dressing, no matter how much you shake it, that will always separate out. An oil spill from tanker demonstrates the petroleum and seawater are not miscible, and that's some of the problem here, is because it's lighter, it's less dense, it causes this cover, and that is not good for aquatic sea life. All right, so here is some more examples of what miscible is and immiscible. So here we have water and carbon tetrachloride. Now, which is on top and which is on the bottom depends on the density of it. The heavier density one will be on the bottom, and the one that's less dense will be on top. So we have lighter water sitting on top of carbon tetrachloride. They both look very clear. However, carbon tetrachloride is carbon with 4 chlorides. That is tetrahedral, and so it's nonpolar because they cancel out. So even though you're dealing with a more electronegative chloride over carbon, because it's very symmetrical, these all are going in this very even directions. It cancels each other out. So this is not, they do not mix. This is 2 layers, immiscible. Now we have carbon tetrachloride with an iodide, and iodide is not polar. So you can see here's iodide in carbon tetrachloride. It dissolves readily in carbon tetrachloride, but not water. Note the undissolved iodide at the bottom. So iodide, this is just what hasn't dissolved in it, but you see that they mix very well. So it goes from a very dark color to mixing together because it's in a sense diluting itself with the carbon tetrachloride. Now sugar, this is sugar in carbon tetrachloride, which is what would be here. They do not mix together. And you can see that. Sugar is very polar, so it dissolves very easily in water, but not in a non-polar solution. So that's why you see this looking like very weird. And then here we have sugar and water, and you can see there's one layer. So you can very well see the 2 layers and the 1 layer, and that's what miscible and immiscible means. Polarity has a lot to do with how we see and use things. So a molecule has a dipole force if it is polar. And to determine a molecule polar, you must determine whether a molecule contains polar bonds, and then determine whether those polar bonds add together to form a net dipole. And we did this in chapter 10. So remember, we had to look at charts and so forth to look at the specific bonds, then the shape of it, and that'll all tell us if we're dealing with something that could be polar or nonpolar. So let's take a look at some examples here. Determine whether these molecules have dipole-dipole forces. So a molecule has a dipole-dipole forces if it is polar. To find out whether a molecule is polar, these are exactly what I just said, and this goes back to section 10.8. And then here's your electronegativity molecules. So looking at this, the electronegativities of carbon is 2.5, oxygen is 3.5. So we have, let me just make this in. We have one pulling in this way and one pulling this way. So by itself, yes, it would be, there would be an electronegativity pulling on this side. However, because it's linear and it's shaped linear, it cancels each other out. So even though there's polar bonds, they do cancel out, which makes this molecule nonpolar, and it does not have dipole-dipole forces. So then we look at B, which is CH2Cl2. So sorry, I didn't notice that it didn't carry over onto the slide to see it for the second one. But there it is, CH2Cl2. So we have electronegativities, and there are formed in 2.5 for carbon, 2.1 for hydrogen, and 3.5 for chloride. CH2Cl2 has 2 polar bonds, and this one's really nonpolar. So we have 2 polar bonds and 2 nonpolar. The geometry is tetrahedral, and I believe it's going to show you there. So they are different bonds, and they do not cancel out. So there is an overall net dipole, and this molecule is polar. Now we're looking at the last one, which is methane. And methane, very easily I can tell you, is not polar. Why is it not polar? Well, one, it's tetrahedral. Two, because it's all in very, it looks very symmetric. And molecules that are very symmetric are not. They all have all the same terminal atoms at the end. So, and the bond and the electronegativity is almost it's close to each other. It's almost negligible. So this is a non-polar molecule, and it does not have dipole-dipole forces, unlike B. Okay, so now we're going to get to hydrogen bonding, and this occurs between the partial positive hydrogen atom in one molecule of water and the partial negative oxygen in another water molecule. Just because you see a hydrogen bonded to something, let me make this very clear, does not mean you're dealing with hydrogen bonding. There are specific conditions that have to be met in order for hydrogen bonding to exist. What are they? Well, actually I found this nice little GIF so you can see this hydrogen bonding. Hydrogen bonding is why water is the way that we understand it as a liquid, when everything else in the same molecular mass is a gas. It's hydrogen bonding that changes everything. So polar molecules contain hydrogen atoms. They're bonded to fluorine, oxygen, and nitrogen. Here are the specific conditions. Has to be bonded to a fluorine, an oxygen, or a nitrogen, but there's more to it. It's not just that. So it exhibit an additional intermolecular force called hydrogen bond. This is a kind of a super dipole-dipole force. It has to be, I'm going to repeat it, has to be bonded to fluorine, oxygen, or nitrogen. A hydrogen has to be bonded to one of these. Has to have a very large electronegativity difference, which you will find in fluorine, oxygen, and nitrogen. Small size of these atoms allow neighboring molecules to get very close to each other. So these are the factors. And when it does, a strong attraction between the hydrogen in these molecules and the F, O, and N on neighboring molecules. So that, let me explain what this is. I told you there are specific conditions, and there are. And hydrogen has to be bonded to a fluorine, oxygen, or nitrogen in that molecule. Then what is attracted to it, what causes the H bond, is there has to come in a fluorine, an oxygen, or nitrogen on a neighboring molecule. So if we look at this GIF here, this is, we have an oxygen attached to a hydrogen, and now another oxygen comes in. This is the hydrogen bond. So just because you see an H bond does not always mean it's a hydrogen bond. It has to have specific conditions in order for this to be met. Okay, so an H in hydrogen fluoride, here we have hydrogens. So here are the specific conditions. It's partial positive, partial negative, and that all causes these hydrogen bonding to occur. This is attached to a fluorine, which then it is attracted to another hydrogen. This meets the conditions of it. And this is very strongly attached. So this is stronger than a dipole-dipole. Here is hydrogen bonding in methanol. So since methanol contains hydrogen atoms directly bonded to oxygen, so methanol is here. We can see we have C. We have 4 H's, and an oxygen. But this hydrogen is attached to the oxygen, not to the carbon. So that meets the first rule. And now it will now be attracted, this hydrogen, to the oxygen on another methanol. So this will occur. Those conditions are met. Methanol molecules form hydrogen bonds to one another. The hydrogen atom on each methanol molecule is attracted to the oxygen atom on its neighbor molecule. All right, so this also affects and it's just another intermolecular force, and this also affects boiling point and melting point, along with dipole-dipole and dispersion. So if we look at methanol here, we have a molar mass of 32 grams per mole, and you can see the structure. So you can see where the oxygen is attached to hydrogen, and then another oxygen can come in and attracted to this hydrogen. The boiling point is 64.7 degrees. The melting point is negative 97.6. However, we have ethane, which is very symmetrical, non-polar. You can see the difference. It is vastly different in melting point and boiling point, and that has to do with the hydrogen bonding. Hydrogen bonding in water, as you can see, forms very strong bonds to each other, and this is why we have water as a liquid. It would be a gas if it did not have this, just like every other gas at the same molecular mass. So water molecules form these strong bonds. The boiling point of water is very high. It's very high compared to other substances with the molecular mass, which is 100 degrees Celsius. So you can just see here more patterns of understanding this. and it has a very low molar mass. So this makes water just so special compared to everything else. Okay, so one of these compounds is a liquid at room temperature. Which one and why? So if it is a liquid at room temperature and not a gas, that means it has stronger forces. And that the stronger intermolecular forces. So we need to figure out which one has stronger intermolecular forces here. So let's look at the mass. They all are almost very similar in mass. So the mass is not necessarily going to tell us anything. We're going to have to look more into what these molecules are. So they all have dispersion forces, so that doesn't count. All three are also polar, so that doesn't count, because where's the polarity? Well, we have an electronegative oxygen here and a partial positive on this side. We have a fluorine here, so there's an imbalance here, even though this is a tetrahedral. And we have two electronegative atoms here that have lone pairs on them, remember that as well, and hydrogens. So so they also have dipole-dipole forces. So they all three have dispersion. They all have dipole-dipole. Hydrogen peroxide, however, is the only one that contains an H bonded directly to a fluorine, oxygen, or nitrogen, which means that if there's another hydrogen peroxide molecule, it can come in and provide that other attraction, and that's going to give it an H bonding, which means that it has a highest boiling point of 3. And if you think about it, we all know that hydrogen peroxide, if you have some in your medicine cabinet, you probably use it on your cuts. So it is a liquid. So that is the difference here, is the H bonding is stronger than the others, that it is a liquid compared to the others, which are not. Note that although fluoromethane contains an H and an F, it is not directly bonded to fluorine. That hydrogen has to be attached to the fluorine in order for that to be hydrogen bonded. So fluoromethane does not have a hydrogen bonding as an intermolecular force. Similarly, the formaldehyde does contain an oxygen and a hydrogen, but again, key thing, hydrogen has to be directly bonded to the oxygen, or it is not an H bond. So hydrogen peroxide has dispersion forces, has dipole-dipole forces because it's polar, and also has hydrogen bonded forces. So ion-dipole forces. Ion-dipole forces exist between something like a sodium cation and the negative ends of water. Because it's an ion, it is attracted to the partial positive and partial negative side of water, just like the chloride ion would be attracted to the positive ends of water molecules. And this is what allows sodium chloride to dissociate, and if they become hydrated around water molecules, hydrate them and prevent them from coming back together. So this is just another little GIF where you can see. But I found a little gift here so you can see what actually happens. So salt goes into the water, and then now the water's hanging out, and it'll start pulling as these start disassociating. The water is going to be attracted to the partial positive or partial negative ends, and you can see the water molecules orient themselves as they are attracted. So you see how they're moving, and then look at the chlorine over here. These move and orient themselves towards the partial positive or partial negative end they are attracted to. So this is what is called hydration, when they fully encapsulate these molecules, these ions. And because water has a bend shape in lone pairs, that's why it's so easy to do that. It can move however it needs to adjust for the partial positive and partial negative ends. Water's polar, we all know that, and that is due to the unequal charge separation, which is a dipole moment. So polarity and hydrogen bonding, on top of, and then with the electrostatic interaction between the charged ion and water, which has a dipole, this allows this ion-dipole interaction to occur. Okay, so let's take a look at a chart here. We have dispersion forces. They are the weakest of all of them. They're also called London forces. They increase with molar mass, and all atoms and molecules have them. Because we have electrons do not stay stagnant. They move around. So this imbalance will eventually happen, and then it'll go away. Dipole-dipole forces are with strength. Only happens in polar molecules. And so nonpolar have dispersion forces, but they don't have dipole-dipole. And they won't have the other ones either. So here we have an example of HCl with HCl. Hydrogen bonding have specific conditions that have to be met. And if you have hydrogen bonding, you most likely have dipole-dipole, and you could have dispersion forces, but you need to make sure and look at every molecule. Ion-dipole forces are extremely strong because this is an ion that's attracted to a partial positive or partial negative end, and they are the strongest of these. Okay, so let's identify the main type, and I'm just going to cheat and go to the end. And so we have a nitrogen with 3 chlorides. that is a polar molecule. Nitrogen has a lone pair on it, and it has electronegative chlorine. So it's a dipole-dipole moment. Hydrogen bonding, we already covered, it has water. Water is a good example of it. Bromine attached to another bromine. This is nonpolar. It has a dispersion forces only, but it does have some kind of intermolecular forces. So remember, the nonpolar molecules do have something. Potassium chloride, that's an ionic bond. And then we have ammonia, and ammonia has hydrogen bonding because those can attach to other ammonia molecules. So on top of this, remember that this is dipole-dipole forces and dispersion. This has hydrogen bonding, dipole-dipole forces and dispersion. This has just dispersion. This has ionic bonding, and this has, and it could have dispersion forces as well. And this has hydrogen bonding, dispersion forces, and dipole. But we're looking at just the main ones that we want to see here. But just remember